of yesterday's lecture, if you recall, the kind of major punchline of the discussion was a special type of coupling between the positional degrees of freedom in a polymer pneumatic and the orientational degrees of freedom. Okay, so we had some density which could vary from place to place, some pneumatic orientation which could vary from place to place, and we argued in the limit of very long chains we should expect some operator that we could call the flux of polymers to be conserved, and the consequence of that was a relationship between gradients of the density and gradients of the orientation. Okay, so in particular, we found that derivatives of the density along the pneumatic director have to be equal and opposite to the density times display deformation. Okay? And so this leads to some very interesting effects in terms of the effective elasticity and fluctuations of the system. And when I ended the lecture, I posed for you this puzzle, and I'll pose it to you again. If you look at the density fluctuations as a function of wave vector, you find some terms that describe these thermal fluctuations that depend on wave vector, but in particular there are terms that will diverge along certain wave vector directions. Okay? In particular, modes which have zero wave vector transverse to the long axis of the molecule, but non-zero wave vector along the z-axis. Okay? And the funny thing is that the offending term has something to do with K3, which we know is telling us about the cost for bending of these filaments or polymers. Okay? So the fact that these fluctuations are extinguished along these lines means that the bending is very expensive for some reason due to this coupling. Okay? And the puzzle was, can anybody explain this to me? And let me see if there are any takers. Still no takers. Okay, I'm going to leave it open. Okay, I think it's in this picture. Okay, so let's see if we can think about what about these modes should cost us an infinite amount of bending energy. Okay, so for today's lecture, we're going to move on quickly to talk about a phase of filaments which is more ordered than the polymer liquid. And this is the columnar phase of chains, okay? And so this is a material that's at higher density or stronger interaction such that the chains have 2D positional order transverse to their long axis, okay? And so in this case, we describe the material in terms of these two types of order it can have, okay? We think about this situation where we have chains, we put them in some reference state, which is perfectly ordered. In that case, it's a parallel array of chains and it's, say, a hexagonal 2D hacking. Okay? And that's the sort of the zero energy state of this ordered structure. And then we sort of take that and we consider fluctuations. Okay? And fluctuations are described by a certain field, which I'll call the displacement field. And the funny thing about this displacement field, even though this is a structure in 3 dimensions, it only has components in the xy plane, say, that transverse to the long axis of the molecule. So it's a 2D displacement of a 3-dimensional material. And that's because this is a funny phase of matter where, at least in the absence of any correlations along the long direction, you're allowed to freely slide the columns with respect to one another. Okay, so that's the liquid aspect of this assembly. So the important thing to realize here is that this in-plane displacement is also inextricably coupled to the orientation for the columnar phase of polymers. Okay, so you'll realize that if I take this in-plane displacement field, not only do I change the spacing between filaments at different places locally, depending on this configuration, but if this in-plane displacement field has gradients along the z-direction. Z-direction is the long axis of the molecules. I also will reorient the molecule. Okay? So to see that, we can think about the reference state of filaments here pointing along the the z-axis and introduce a displacement field. Say we'll write this as theta times z. Okay, so that the new position of the column adopts this configuration. Okay, so I displace the top to your right and the bottom to your left. Okay, so I simply have a linear slope, and that means that not only have I displaced the position, but I've also tilted the filament. Okay. So the displacements, which describe positional fluctuations, are depending on their gradients along z. They also correspond to tilts. Okay, this is the analog of the conservation condition for long chains. So this has consequences for the fluctuations of columnar material, and so I'm just going to kind of go through the similar arguments we did for the polymer pneumatic, just to get to the sort of analogous punchline. And I'm not going to spend too much detail on it, but I just want to kind of get to a key difference. So again, we have some elastic energy that in principle could penalize splay, twist, and bend, just as we did for the polymer pneumatic, because this structure is imbued with long-range orientational order. Okay, and at the same time, there's some new type of elasticity that penalizes deformations of the lattice order. Okay, and so this elasticity I've written as F of solid. Okay, and it's built out of an object which looks very familiar from this morning's lecture, although the notation is a bit confusing. Okay, so this is U of ij, which is the partial first derivative di uj plus uj ui. Okay, and so this describes deformations of this lattice packing. Okay, so in particular, you could show that if you start with a nice hexagonal packing, okay, and you deform it in certain ways, that corresponds to certain non-zero strain components. Okay? So, for example, if we, this is the x-axis, we stretch it out along this direction, okay, that corresponds to uxx not equal to 0 or greater than 0, so I've stretched it along the x direction. You could just check this if I put it in x, linearly x-dependent displacement field. Likewise, I could take this structure and stretch it along the y direction. So now it's a bit taller, and you can easily imagine the distance between the filaments here have changed somewhat. Okay, so here's uyy is not equal to 0, and then finally, if I take this structure and I shear the top with respect to the bottom, and so I can do something like this. Okay, I've sheared the top to the right and the bottom to the left. Okay, in this deformed state. I've introduced some shear. So what you're supposed to see in this picture is that the top has moved to the right with respect to the bottom. Okay. So the three independent components of the strain tensor basically measure these types of three deformations. Okay, and the simplest type of elasticity energy you need to describe is basically square penalties for these deformations. Okay, because basically they describe within the appropriate symmetry all the different ways that I've changed the local spacing between the nearest neighbors in this packet, which wants to be uniform. Okay. So to linear order, again, I said that there's this symmetric first derivatives, and this is what you would find for any 2D crystal. But again, these two order parameters are coupled inextricably. And again, I don't want to go through the details, but and you will have these slides. We can play the same game that we did yesterday. Okay, we can convert this whole picture to Fourier space and look at the fluctuations both in terms of the tilt and the position, decomposing both of these into their longitudinal and transverse components. Now, the displacement field is not, the density was a scalar, okay, quantity that could fluctuate. The displacement is the position in the xy plane, so that's a two-component field. It also can be decomposed into transverse and longitudinal modes. We can go ahead and plug these into these two different types of energy expressions. This is the same formula we saw yesterday for the Frank elastic energy decomposed into longitudinal and transverse modes. I think there's a typo, maybe that's a typo, or it's just I can't read standing that close. And the positional elasticity also decomposes into transverse and longitudinal modes. The longitudinal mode couples to this constant lambda, which is called a Lemay coefficient, whereas the transverse mode is the one which is sensitive to shear. Okay, so this picks up the shear modes. In any case, they're both here, and what we're going to do, what we would do, actually what I should have done is cited Jonathan Sellinger's paper on this from 1995, where they did this. Basically, we take this geometric condition where the z derivative of u is related to the in-plane tilt, okay? And then we solve for the in-plane displacement in terms of the tilt and shove it back in here, okay? And that's it. And then what we're going to be left with is an effective free energy that depends only on the pneumatic fluctuations with the displacement sort of implicitly carried along. Okay, it's the same identical formula. And if we did that, you see I think I've kind of smeared that out. What you would find is the following effective free energy. It looks the same as the pneumatic, okay, but I have these primes on K1 and K2. So in fact, what I end up with is a new theory for the pneumatic, where the Frank elastic constants for splay and twist have become renormalized. So previously for the polymer pneumatic, it was only the splay constant that was renormalized, right? Because splaying the configuration caused the chains to stretch apart from the top and the bottom. And we see that we have this same kz dependent term. So as kz goes to 0, the cost for splay goes to infinity. Again, meaning uniform splay is impossible. What we find here that's new is that the K2 constant, the constant for twist, also diverges. Okay? And the fact that twist is now infinitely expensive has something to do with the difference between a polymer liquid and a polymer solid. Right? Now that I have not liquid-like order in the transverse direction, but I have really true two-dimensional long-range order, is leading to the divergence of this other elastic constant. So as I go from a regular pneumatic to a polymer pneumatic, the cost for splay goes up as the length of the chains goes to infinity. As I go from a polymer pneumatic to a polymer columnar phase, the cost for twist also goes through the roof. Okay. So what's going on there? So this is actually roughly not too hard to understand with some pictures. Okay, so here's our columnar phase. And again, remember that the orientation of these chains is coupled to the in-plane displacement. And the idea here is that somehow if I try to impose a uniform, simple twist on this structure, it's going to cost me an infinite amount of energy. That's what the divergence of this elastic constant signifies. Okay? So let's take our packing of columns, and let's just try to twist it. Right? What's the big deal? Okay? So we're going to impose a cholesteric twist. I'm going to twist the chains in the front to the right and the chains in the back to the left. Presumably, so basically cholesteric twist means that n dot curl of n is uniformly equal to some number. I'll just choose it to be Q naught. And let's see what I do. What you can see now is that as I tilted the chains in the front to this way and tilted the chains in the back that way, as I move from the bottom to the top, I get a gradient of the shear. Okay? I have to shear the top, the packing at the top, and this way, okay? And at the bottom, I have to shear the packing in the opposite way. Okay? So now there's a shear and a shear stress, as well as a shear strain, which is linearly changing as I go through Z. So I have to introduce, at least in this simple mode of cholesteric twist, I have to introduce long-range shears. And it's the energy cost of these long-range shears that make simple twists impossible. Okay? So I can't have any simple twist in a columnar material because of this coupling between orientation and position. So this should be a problem, especially since I told you what we're going to talk about is what chiral assemblies of chiral filaments do, right? They want to twist. Okay, they're chiral, and by virtue of that, they like to try to rotate the relative orientation of nearest neighbors in a handed way. Okay, they somehow have to live with this fact, and I just told you that it's impossible to have a simple holosteric twisting of a columnar material. So what indeed might happen? So what we're going to talk about is a bit more of a complex texture, which somehow deals with this compromise. Okay, it's in some sense it's an exception to the rule that I just told you, but in a more accurate sense, I think it sort of gives you a more refined definition of exactly what modes are prohibited and exactly which modes are allowed. So what we're going to talk about is this question of the thermodynamics of a structure like this, okay? And I call this a double twisted texture. I'll tell you a little bit more why that's true, but you can basically think of this as a bunch of tubes. I pack them together in some two-dimensional way, or they pack themselves together through cohesive interactions, and then I simply twist the top with respect to the bottom, okay? And every filament you can see rotates around the center of this bundle. And so there's sort of two motivations. We've been thinking about these problems for the last couple of years, and there's two sort of primary motivations that we want to understand. The kind of the nature of the ordering and the interplay between the ordering and the thermodynamics in this material. One of them is that these sorts of structures form all over the place in biological filament assemblies. Okay, and so here are just a few example fibrin. Certain collagen fibrils are observed to be twisted, and even certain types of biological filaments which don't form in healthy individuals. So these are called sickle hemoglobin macrofibers. So the sickle cell mutation actually causes these hemoglobin proteins to assemble into chains, but through their interactions, because these are built out of chiral subunits, they also spontaneously twist around one another, sort of form these braided structures. So these are these three examples, and we'd like to try to understand what kind of a simple physical model might tell us about the sort of universal behavior of these sorts of structures. But from my point of view, I'm really interested in this because this is what I would say is sort of the simplest yet non-trivial example of the frustration. What I'm going to tell you is an intrinsically geometric frustration between the positional order of this assembly and its orientational order. Okay, so if you remember nothing else from this lecture or the next lecture, you have to remember the following fact. There is no amount of twist that I can put in this structure such that I can have all the filaments in the cross-section be evenly spaced. Okay? Any amount of twist makes it geometrically impossible to space filaments evenly throughout the cross-section. Okay? So that means that there's a fundamental, unavoidable conflict between chirality and assembly. So we'll talk about this in sort of two flavors today, today and tomorrow. So we're going to be talking about the structure quite a bit. Let me define a few parameters that will come up. So capital R will be a lateral radius of the structure, and we'll parameterize the twist by this parameter capital omega. And you can think of the twist as, omega as the rate of twist, or the rate of helical rotation along the long axis of this bundle around the center. Okay, so 2 pi over omega is the pitch of each of these filaments, and they each follow helical paths. Okay, and the product of these two things, omega times r, is related to this angle theta at the outside of the bundle. So let's see. Does anybody recognize this structure? Have you ever seen a schematic that looks like this in any other context of liquid crystalline materials?
Color-strict double twist, blue faces have...
So this texture is sometimes called the double twist cylinder, and it's a sort of a structural element of an exotic phase that is becoming re-emerging in terms of applications for photonic materials. And this is a phase that forms in chiral liquid crystals just at the point of melting, okay, as we go near the isotropic transition. And so what this phase is, okay, one way of trying to understand the phase is the following. If you look inside of this double twist tube, okay, or this double twist structure, which I've kind of abstracted as a kind of a nested shells of filaments, and we imagine kind of going from the front of this bundle into the center and out to the back, okay, what you can see is that at the outside I'm tilting here to the right, but as I move, say, to the purple filament, the purple layer, I tilt a little bit more in, and move a little bit further into the red. Finally, I get into the center of the bundle and I'm sticking straight up, okay? That's the filament which is along the center of rotation. Then as I move to the back, I twist the other way, okay? So, in fact, as I drill from front to back, along the radial directions, there's something like a cholesteric twisting, okay? But that cholesteric twist is happening along every radius. And so, if you think about what's happening at the center of the bundle, it's like you have a cholesteric going in two perpendicular directions, so it's double twist, right? It's two times as good. Okay, so this is why chirality likes this structure, right? It's favorable from the point of view of expressing the end up curled end, which is how the Frank free energy knows about the twist. Okay, so we should expect some structure like this could be a possible candidate. Okay, so now I'm going to switch to the board and try to tell you why, if twist is impossible or infinitely expensive in a columnar assembly, somehow double twist is not. Not only is it not infinitely expensive, it's quite cheap. Okay. Good. So we'll call this double twist, call it double twist bundle, say. And the filament positions rotate around bundle center. Which for me is going to be the z-axis, okay, at a rate omega, okay. So I go the pitch, I go around one time the bundle center. So what is the displacement field that describes that deformation? So if I look down from the top of my bundle, so here I'm looking down the center of rotation, a filament that used to be before the twist at this position has been rotated to a new position. Okay. And the displacement is simply that rotation. You perp on x. So what is this angle? If the rotation rate is omega along the bundle, as I move up, the position is moving around like a clock. So this angle is omega times z. Okay? So as I increase, I look at different vertical slices, the position of the filaments just goes around and around. It's a simple rotational displacement. So we're going to consider this for cross sections which are near z equals 0. That's just all the results that I'll derive are general, but based on it. But it's an easier way to study this. Okay, so this simple rotational displacement is very easy to write down. Okay. So minus y in the x-hat direction plus x in the y-hat direction. This is purely rotation in the two-dimensional plane. Okay. Otherwise, we could call this r times phi hat. Okay. Where this direction is phi hat is the azimuthal direction. Okay. Just introducing polar coordinates, if you like. So again, we have our free energy function. Which depends on strain. Okay, the first symmetric derivatives of u. Okay, so what's important to realize is if the strain is 0, the energy cost is 0. Okay? So let's check the strain that's generated by this rotational displacement. Okay? So first, let's check uxx, which is dx ux. So here we go. We're looking at the x component. What is the x derivative of u? X? 0. I'm going to get to your question. Yes?
I'm just wondering what the strain indices.
What the...
IJ.
You're checking my calculation on the fly. Very good. So this would be d I uj plus d j ui, where I and j refer to x and y directions. Okay, so the strain along x is 0. How about the strain along y? Which is the y derivative of the y component? 0. Okay, so 2 out of 3 are 0. Now remember, the reason that twist was so expensive for columnar phase is because it generates shears. Okay, so shear was the problem. I shouldn't worry so much about these extensional strains. I should expect them to be 0. So let's look at the xy component, which is 1/2 dx uy plus dy ux. Okay, so what is dx uy? It's omega times z. Sorry, this should not be z hat. Too many hats. Too many hats on the right side.
Omega z.
It's omega z plus omega z. Okay, so what is dy ux? Is the x component? Minus omega z. So this is 0. Okay. This deformation to linear order in this displacement of my strain causes no strain. Okay, there's no strain, there's no energy cost. Not only is it not infinite, it's 0. Okay, as small as you could possibly be. Okay, so what have we missed? Something must be horribly wrong, right? This says this deformation causes 0 energy. So, first of all, it's important to point out why we should have expected this deformation to cause 0 energy. Now, the elastic energy of a 2D solid, like a piece of paper, right? It's kind of a 2D solid, roughly. If I take the entire 2D solid and I rotate it rigidly, it doesn't cost me any energy, right? Rigid rotations have to be a symmetry of the elastic energy. Okay? And in this double twisted bundle, every cross section is simply rigidly rotated, okay, by a different angle. Yes, sir?
So if we have considered the nonlinear term in the strain?
Well, yes, it has something to do with a certain nonlinear term. So there's different nonlinear terms. So one nonlinear term is the type of nonlinearity I would have to write down if I had a pure two-dimensional material. Okay. So you would see, if you put in the exact displacement field, which only holds up for small z, okay, this form that I've run, and try to calculate the strain, it wouldn't be 0 unless you included a certain nonlinear term, okay, which is second order in plane derivatives of u. But if I did include that nonlinearity, it would be 0. Okay? So if I wrote down the right thing in the first place, I would get 0. Okay? That's not what I'm missing. I'm missing something else. And so let me tell you about what we're missing. Right. Okay, so here we go. Here is our free energy. And now, I'm sorry, I didn't mention this before. I've changed my free energy to be the free energy of a chiral system which wants to twist at a certain rate, Q naught. Okay, so n dot curl of n wants to be non-zero. That's the game, right? How can we structure this thing in such a way that n dot n is as close as possible to this constant, which is set by microscopic structure. And the issue is that this linear strain tensor doesn't work, and in fact the linear strain tensor, there's something wrong with it. The nonlinearity that we actually have to consider here, we're obliged to consider here, is not the nonlinearity of in-plane displacements, but it's a nonlinearity associated with the coupling between the displacements and the tilt. Okay? So, in addition to the symmetric first derivatives, di uj plus dj ui, there's a geometrical term here, minus ni nj. Okay, ni is just a filament tilt, and the ij components are just the x and y components. Okay, and let me just tell you what this thing does. I don't want to spend too much time going through convincing you that what I'm saying is true. It makes sure that the distance that the elastic energy is measuring is not the distance between the filaments in the xy plane that I happen to write down my theory in. Okay? It makes sure that it's measuring the distance of closest approach between the filaments in the deformed state. Okay? So that is to say, if I have parallel filaments, they're initially pointing along z, I can change their spacing in two ways. I can keep them parallel and change their spacing by straining them in the x and y plane. Okay? Or I can keep their spacing in the xy plane the same and tilt them. Okay? And you'll see that the true distance of closest approach will decrease purely under tilt. So this is an example of what's known as a geometrical nonlinearity. It's not a nonlinearity that appears because of some physical constant. It's a nonlinearity in the appropriately symmetric definition of the strain. Okay? So another way to argue that this term has to be there is that we have to have an elastic energy that's invariant under taking this entire bundle of initially parallel filaments and uniformly rotating it around some axis in the x and y plane. If this wasn't there, there would be some fake energy cost. So, in fact, in this deformation, there is some complex texture. Oh, we're not doing that today. And so we'll leave that up. So what is the cost of this coupling between tilt and strain? So the nonlinear strain minus ni and j includes this extra term that says that filament spacing can decrease purely through tilt. Okay, and we already showed that the linear definition of the strain gives me 0. So this is 0 for the pure rotation. Okay? So all of the cost, at least in this sort of naive theory, is coming purely through the fact that I'm changing the distance between the filaments by tilting. Okay. So in particular, if we calculate the tilting of the filaments, okay, that's dz of u. U is down here. Okay, so dz of u is just omega times r times phi hat. Okay. Omega r phi hat. So if I were to look down at the top of my bundle, okay, and I look down the center, that filament's pointing straight up at me, but as I move out from the center of the bundle, I see that the in-plane projection of the tilt will increase as I move away from the center. Okay, so it increases with the radial distance and it tilts along the azimuthal direction. So, the component of the strain that I think I should worry about is the component of the strain in the phi direction. Okay, so I can change my coordinates. Instead of x, y, I can work in strain components of the polar coordinates. Okay, so this is going to be minus 1/2 times delta n phi squared. Okay, and that is minus omega r squared over 2, which is not 0. Okay. So what this minus sign is telling you, the fact that it's negative, is that the filaments are getting closer together. Okay? Because the filaments are tilting towards one another at the outside of the bundle, they're actually generating compression in this structure. Right? There's a sort of an overcrowding effect where these filaments at the outside of the structure, okay, are not, they want to be this close apart, but they're actually this close apart, which is smaller by a factor, the cosine of that angle. So this is what you would call a compression along the hoop direction. And so what is the physical consequence of this? Okay. So let us go back to this elastic free energy, and we'll do a naive calculation where we simply take this strain. In this naive calculation, the only non-zero component of strain is in the phi direction. Okay, and we'll plug that in here and calculate its cost. Okay, in the elastic energy. And I will write this naively to make sure highlight that we're doing something incorrect. So what we should do is integrate the elastic energy density, okay, which gives me a lambda times u phi squared plus 2 mu times u phi squared. These are the only non-zero terms in the elastic energy. Okay, and now to simplify things, this volume integral, okay, the integral along length is easy. That's just going to give me a factor of L. The integral around the angle, phi, is just going to give me 2 pi. So what I'm left with here is 2 pi L times lambda, plus 2 mu divided by 2 times the integral over r dr of omega r squared from 0 to capital R. Okay, capital R is the outside of the bundle. And if I did this right, our naive theory would give us, we'll get a 4 from integrating r cubed. Yes? Yes? Omega r squared over 4 times pi r squared times L. I like to group this part together because that's the volume of the bundle. Okay, so the volume of the bundle times some factor that depends on, sorry, I did something wrong here. This should be 4, right? Because I'm squaring omega r squared, which is already squared one time. Okay? And I think I must have forgotten a factor of 2 from this. It's always good. It's always good to correct your notes on the fly. Okay. So what I should get is a factor of 6 down here, and this should be omega times r to the 4th power times pi r squared times L. So r to the 4th power plus times r squared, that's r to the 6th. Okay, I think that checks out. So now what I see is that I get an elastic energy that's highly sensitive both to the twist as well as the radius of the bundle. Okay? So a direct consequence of this geometric frustration and this geometric nonlinearity is now that the energy cost of growing this structure becomes highly sensitive to the structure and its size. Okay? And the consequences of this in terms of the assembly thermodynamics are very important. So, okay, so what's wrong with this naive calculation? All I did, I took this simple rotational displacement, okay, I evaluated the strain, I plugged it in. Again, using the facts that we already checked by hand, that for this rotational displacement that there was no strain. So imagine that you're living in this bundle. Okay, you're one of these filaments, especially the ones at the outside. Okay, and somebody comes along and grabs this entire collection of filaments and twists the top with respect to the bottom. These filaments at the outside suddenly become squished. Okay, they're running out of space, they're overcrowded, and they start pushing on their neighbors. Okay, they're pushing on their neighbors, pushing on their neighbors, pushing on their neighbors. What's going to happen? Well, it could either stop twisting, okay, but one thing that can happen is that the structure can dilate. By expanding radially, you can make a little bit more room with your neighbors along this azimuthal direction, but then all of a sudden you get too far away from your neighbors along the radial direction. They start pulling you in. Okay? So there's a secondary sort of deformation that takes place where this is not zero. Okay, that does a better job of minimizing this elastic energy than the initial rotation. Okay, and we could do that exact calculation, but we're not going to. This is a very nice exercise if anybody would like to get this result. I've done it wrong many times before. Okay, it's almost the same thing, just with a different prefactor. Okay. Okay, so we still have omega r to the 4th times the volume of the bundle. This factor of y here is not directly proportional to the shear modulus. It's equal to 4 mu times lambda plus mu over lambda divided by 2 mu. Not really important, okay, but one can do these calculations. For anybody who's interested in these sorts of things, this is what's known as the 2D Young's modulus. And there's a reason why it's that, but we'll move on. Okay, but the important idea here, again, is that we have a size-dependent elastic energy cost. Okay? So now let's combine this elastic energy cost with the energy cost for twisting and bending. Okay? We'll start with twist, because that should be easier. Okay, so what is the holospheric twist of this pattern? Okay, so there's the pattern up here. Let me write it again using the xy coordinates where it's easier to calculate. So this is minus y in the x direction plus x in the y direction times omega. So the holospheric twist is dx delta ny minus dy delta nx. Okay, so dx delta ny is what? So the y component of the twist is x times omega. So the x derivative is omega. Thank you. Okay, minus the y derivative of the x component. The x component is minus y. So the y derivative of the x component is minus omega. So minus omega. 2 omega. So the 2 is the double in the double twist. Okay, it's twisting along two perpendicular directions, the x and y direction. And so this tells you that the twist elastic energy, where I substitute this expression in, can be written in the following way. After I do this integral over the area and the length, and I'm just going to summarize the result for you, because I want to get to the punchline. Okay. So, okay, I had to define a new constant here, omega 0. Okay, that's equal to q0 over 2. Okay, that factor of 2 is everything to do with this factor of 2. Okay, so if there's a preferred cholesteric twist of q naught, right, so 2 pi over q naught is the preferred cholesteric pitch. The preferred double twist pitch is half that. Okay, so there's a factor of 2. But what does this say? It says that the chiral energy of the system, unlike the elastic energy of the system, it wants the double twist to be non-zero. Okay? And it grows with r, but only as the volume. Whereas the elastic energy grows faster than the volume with r. Right? It wants omega to be 0 and r to be 0. Or the combination of the two. So finally, I'm not going to go into the calculation. You can check that this is the result you would get if we calculate the bending energy. Good. Okay, so we'll have to stop. So the bending energy, after we go through the similar steps, is, of course, proportional to K3 pi r squared times L, the volume of the bundle, divided by 4 times K3, also proportional to the fourth power of omega, but a slightly different power of r. Okay. So, this is the final result of this, this calculation, and we have everything we need. Okay, and so I'm just going to rewrite everything I wrote there back on this board. And we're going to study what would happen if we had a bundle which was assembling with this free energy. It has some chirality, it wants to twist, but it has to pay a cost. And how does the structure of this bundle change as it changes its size? And how does its free energy change as it changes its size? Okay. So the total free energy density, which I'll call F star, and define that to be the total free energy divided by pi r squared times L. So that's the sum of the elastic energy, the twist energy, and the bending energy. Okay, let's see. I'll first write the twist term. Apparently I get a 4 there, 4 times K2. Slightly obnoxious, but okay, so 4. Their bending energy divided by the volume. So I have the bending energy density, which is K3 over 4 times omega to the 4th times r squared. And finally, the elastic energy over the volume, which is y over 128. Remember, this is just the elastic modulus times omega r to the 4th. So we have these two different types of terms here. Okay? On the left, this is the form of the, let's say, the chirality. Right? Chirality wants the bundle to twist at some non-zero rate. Okay? On the right-hand side, these are mechanical penalties. Right? This is the mechanical penalty this assembly has to pay if it wants to maintain some non-zero twist. The mechanical cost. And there are two important distinguishing features of these mechanical penalties. First is that their energy is always minimum when there's no twist, right? It's always cost energy to to either bend the filaments if I want to twist it, or stretch them apart or push them too close together if I want to twist that. Okay, so these terms are always minimized by omega goes to 0, and they grow stronger and stronger as the size of the bundle gets larger and larger. So in terms of the free energy density, the effect of chirality, it always wants omega to be non-zero, okay, but it doesn't seem to depend its strength or its effect on the size. So without doing anything, right, so what would we do? What we would do is we would imagine a new problem where we fix the radius of the bundle, and we ask how much would this bundle want to twist? What omega would it want to have given this generic form of the free energy? And so we minimize this expression over omega as a function of r. And we could do that. There's a cubic polynomial equation in there that we have to solve. But let's just think about it for a few minutes and try to understand what are the non-trivial properties that emerge from the competition between chirality and mechanics of this structure. So, all right, what do we think the minimal energy configuration will be when the bundle is very small? So as the bundle gets smaller, what happens to the relative importance of these two terms? Say that louder. So the mechanical costs are always less important as r goes to 0 compared to chirality. Okay, so what's going to happen? What is the minimal energy state as r goes to 0?
Just maintaining your chirality.
It's just omega naught. It's what it wants to be, right? So as r goes to 0, omega is going to go to omega naught. It's going to twist as much as the molecular structure tells it to. And this also implies that the free energy density in this limit also goes to 0. Right? This term could be 0, this term is 0 because r is 0. Okay? Now let's think about the other limit. As r goes to infinity, okay, these terms become very important. Okay, they become arbitrarily important, while the magnitude of the chiral energy stays constant. Okay. So what happens to the equilibrium twist in the limit that r goes to infinity?
Becomes 0.
Say louder.
Becomes 0.
It becomes 0, right? There's no way to maintain a finite energy density with any non-zero value of twist. Okay. The mechanical cost to maintain a finite amount of twist as the bundle becomes large is prohibitive. Okay, so as this structure grows, it undergoes a structural transition. Okay, a small bundle will twist at a rate which is predetermined by the molecular interactions, but if it wants to grow beyond a certain size, okay, it's going to have to untwist. In this case, the mechanical cost is going to be non-zero, but I'm still going to have to pay some cost. Okay? So if omega is 0, there's still some cost to not twisting at the rate that the chirality wants. Okay? So there's a finite free energy density cost. Okay? Due to the fact that the molecules want to twist at a rate omega naught, but they're not allowed to because of the mechanical cost. Okay? So in this limit, it has to untwist. Okay? And it will pay some finite energy penalty, but it's a finite energy penalty, right? Far better than an infinite energy penalty. So now we could imagine, you can check this. If I look at the equilibrium amount of twist versus the preferred amount of twist, okay? If the bundle was twisting at the rate that chirality demanded, okay, it would fall along this line. And it does that for a small size. but it always twists slightly less than that, and eventually it will peel away. And you can check that for large values of chirality, eventually it twists at quite a more modest rate than what chirality demands, and in fact, it also the degree of twist at large sizes, not insignificantly, becomes dependent on size. Okay. So at large twist, at large twist and large size, eventually the optimal equilibrium twist goes down much below the chirality preferred value. So we see something very interesting. The actual structure of this of a bundle evolves in a way that changes both as it changes its size and its chirality. Okay, so now let's go to one last step and ask ourselves the next question. Okay, so this is what we would find if we ask how twisted would a self-twisting bundle be if it had a certain size. Now we can ask the question, how big would a self-twisting bundle be if it could choose its size? Or put another way, if we consider a problem where these fibers or filament bundles are self-assembling in equilibrium and their equilibrium radius is determined not only by the minimization of the free energy over the degree of twist, but also over the size, what is going to happen? So, in order to understand this, we have to add one more physical ingredient. Okay, so here, the total free energy will include not only the size-dependent energy of the chiral elasticity, okay, but it will also have to account in some way for the cohesive interactions of this structure. Okay? So, if we consider a bundle which is composed of many, many filaments, there's a certain density of cohesive interactions in this structure. Okay? So, what do we have here? Well, of course, there's some, let's say, free energy density per unit volume of forming a bundle. We'll call that minus epsilon. Okay, you can think of this just as simply the attractive interactions per unit volume. But these filaments at the outside of the bundle have fewer interactions. Okay? So there's less cohesion at the surface of the bundle because there are fewer nearest neighbors for filaments at the bundle. Okay? And that effect introduces what's called as a surface energy. Okay? So there's some penalty proportional to the surface area of the bundle, 2 pi r times L, times some surface energy. I'll call that sigma, and then we're going to calculate this per unit volume. Okay? So the surface energy wants to minimize the amount of surface that's exposed at the sides of the bundle. And yes, there are tops and bottoms, and I'm not going to worry about that. Okay? As the length of the bundle becomes very large, L goes to infinity, the amount of surface at the sides of the bundle is much more important than the top and the bottom. Okay, so this, in the end, reduces to 2 sigma over r. Okay? So on one hand, we have this chiral elastic energy. It has some certain radius dependence. It's 0 for a small bundle, and it increases to some finite amount for a large bundle. On the other hand, we have the surface energy. How does the surface energy change as the bundle gets fatter and fatter? Does it go up?
It goes down.
It goes down as 1 over r. So the total energy now has these 2 contributions. On one hand, we have the energy of the chiral elastic energy, right, that wants the bundle to twist at a certain rate but can't tolerate the misfit at large bundle sizes. And this looks schematically something like this. It goes to 0 at r equals 0, when the twist is the rate it wants to be. Okay? But as r goes to infinity, the bundle has to untwist because of these mechanical costs. Right? And it can do so, but it's going to pay a finite energy. Okay? So as r goes to infinity, eventually the chiral energy is going to cost K2 times omega naught squared. The energy cost to the cohesion to untwisting the filaments from their twisted state. So I have a monotonically increasing function of r for the chiral elastic energy, and I combine that with the surface energy to omega over r, which is monotonically decreasing. Okay, the surface energy wants the bundle to be as big as possible. This minimizes the volumetric surface area of this growing structure. So what happens when I put them together? A monotonically increasing function with a monotonically decreasing function. So let's imagine the limit where surface energy is 0. Okay, this is my free energy profile. It just goes from 0 to something positive. But then I make some small surface tension. Okay. What I would expect to see, something like that. As I increase the surface energy, eventually the divergence at small r grows to be very big until I reach a critical surface energy. Let's call that E sub c, that I'll label here, and then eventually I may have a surface energy that looks like this. So now this is what I would get for increasing sigma. So what do I expect down here? So what does this minimum mean?
You'll be in an in-between state?
It's an in-between state, and most importantly, it has an equilibrium size which is less than infinity. Okay? It's bigger than 0, but less than infinity. So I find that for small enough surface tension, below some critical value that will depend on these parameters that I'm happy to tell you, this structure will grow to a certain size, which is in principle arbitrarily much larger than the single unit, but less than infinity. As I increase the strength of cohesive interactions and the surface force, eventually I reach a point where the energy of a finite set of finite structures is degenerate with the energy of infinitely sized bundles. And beyond that point, the lowest free energy state becomes the untwisted infinite. Okay. So I'm just going to summarize here, and we'll talk tomorrow about other possibilities. But as I do, I really want to emphasize there's something should be very problematic about this phenomenon that I'm sketching to you. So I went ahead and sketched a little phase diagram, and you can check that this is right. So it turns out one can reduce the appearance of a finite size equilibrium bundle versus an infinite size cluster in terms of only two quantities, one which is related to the twist, divided by the elastic modulus. Okay, so I wrote that as K2 bar. And on this axis, you can introduce another parameter, K3 bar, which is the bend constant times the twist times a certain power of the surface energy. Okay, so these are the two parameters of this phase diagram, and separating two regions of this phase diagram is some curve. If you want, you can check that this curve is roughly K3 bar goes as K2 bar cubed. And what do we find? Well, what we find for small values of K3 bar, which are small values of the surface energy, we have finite size twisted bundles. And for large enough values of the surface energy, we have infinite or bulk untwisted assemblies. Okay, so indeed we find that the competition or interplay between chirality and the mechanics, both in terms of packing the filaments and bending the filaments, leads to unusual thermodynamics. But what I really want to emphasize here, that should be a major sort of puzzle, is, this is a system where these filaments are interacting through purely short-range interactions. Okay, every filament is only interacting with its neighbor. Okay, sticky finite-range interactions, and yet somehow we have this range of assembly where the structure knows how big it's supposed to be. So secretly, through this geometric frustration between the twisting of these filaments and the packing, there's some sort of long-range mechanism that's mediated through the elasticity that gives you an effect, some way that the self-assembling system can measure how big it's supposed to be. So this idea was not, we're not the first to think about it, but this idea has kind of attracted some attention in the context of these biological filament assemblies, because again, we have all over the place many types of cell tissues and intercellular specializations, these self-assembling bundles, right? And in the context of biological physics, which surely is lots of problems of non-equilibrium processes, we always have to ask ourselves the question, who's doing the measuring, right? When some structure is supposed to be remodeled to grow to a certain size, how does it know that it has reached that size? It's not as if there's somebody inside of the cell saying, okay, you built a bundle that's 42 layers big, now you should stop and build another one. This is really a mechanism which may be available, may be adapted for, I don't know, that the structure can measure itself, okay, as it's assembling. Okay? And what I wanted to tell you is that this is really an anomalous class of self-assembly. It is very unusual. What we usually expect is either a dispersed state or a macroscopic precipitant as the two limiting cases of thermodynamic equilibrium. Here, you're allowed a third possibility through geometry. So, okay, so that is the end of what I want to tell you for this lecture. We'll talk a little bit tomorrow about other possibilities that these systems may relax this frustration, right? Other more complicated possibilities. So let me take any questions that remain, and we'll have some coffee.
Those really is nice. Thinking and
Yes.
some questions during coffee, of course, tomorrow, whenever. No certain questions now. Certain questions now.
So we start like 10 past 4.
Should we? Yes.